We've learned enough about physics to send humans to the moon. We've discovered that DNA carries our genetic information. Scientists have even gotten closer to solving the mystery of whether cats can behave as both solids and liquids. But there are still some basic questions we haven't answered, including these frustratingly persistent scientific mysteries.
Those friends who did not subscribe our channel, subscribe the channel and press the bell icon for our latest video.
1. Why we cry. Some of us tear up watching a sad movie. Sometimes, we're so happy that we burst into tears. But according to science, crying in response to intense emotions doesn't seem to be a useful behavior, and it might not have a biological purpose. What science does know is that not all tears are created equal. The chemical composition of the tears produced when we cry, which are called psychic tears, is slightly different from the composition of the tears that lubricate and help expel foreign bodies from the eyes. This has led some to theorize that the chemical makeup of psychic tears makes them emotionally healing. But evidence showing that the chemical differences have substantial psychological effects, let alone that such effects explain why crying evolved, is lacking. And that's not where the theories end. Some evolutionary psychologists think that crying may have evolved as a distress call that brings help. In a 2009 paper, one researcher suggested that tears may signal submission and helplessness by blurring vision, which prompts others to aid, or at least not harm, the crier. But other researchers have pointed out that we often cry after a stressful situation has resolved, not while it's in progress and we need to signal for help. It's also typical for people to avoid crying publicly and to look unfavorably on those who do. In any case, these hypotheses, like most in evolutionary psychology, are difficult to test. 2. How to cure hiccups. Maybe you hold your breath. Maybe you chug water. Unfortunately, nothing has been found to reliably eliminate hiccups, despite the overwhelming number of folk remedies on the internet. This sad state of affairs is likely due to insufficient research. Serious cases of the hiccups are rare, and the mild cases are brief and don't usually cause problems. Most of the treatments for severe cases of hiccups, doses of sedating antipsychotics like haloperidol, vagus nerve stimulation, digital rectal massage, aren't exactly things you could try on your own. For now, you'll have to endure hiccups or stick with unproven, but usually harmless, solutions. At least they give you an excuse to eat peanut butter by the spoonful. 3. How general anesthesia works. As you're rolling into surgery, you probably assume that your doctors not only know how to perform the procedure, but understand how the drugs that knock you out actually do so. But you'd be wrong. Scientists do know that local anesthetics like Novocaine block pain signals before they reach the central nervous system by altering the function of specific proteins on nerve cells. But the molecular basis of general anesthesia is more of a mystery. These drugs seem to interfere with the functions of a variety of proteins on nerve cells in the central nervous system, but how they accomplish this is not well understood. General anesthetics come in a variety of types, and they likely don't all work the same way, so developing models of how the compounds work on the molecular level may continue to be a challenge. 4. How Tylenol kills pain. A layperson taking Tylenol to relieve pain might think it works like NSAIDs, non-steroidal anti-inflammatory drugs, such as ibuprofen and aspirin, which block some enzymes and, in turn, the pain and inflammation causing chemicals they produce. But that's not the case. Acetaminophen, the active ingredient in Tylenol, seems to need specific chemical conditions to work on those enzymes. And it doesn't appear to reduce inflammation as the NSAIDs do. Some researchers think acetaminophen may alter the way pain is perceived by interacting with certain proteins on nerve cells, possibly including serotonin receptors, cannabinoid receptors, opioid receptors, and specific channels on nerves in the spinal cord that transmit pain and itch signals. Acetaminophen byproducts have also been shown to activate these channels rather than shutting them down, further complicating the question. 5. Why we sleep. Too little sleep impairs thinking in the short term and increases the risk of several serious diseases in the long term, while complete sleep deprivation is fatal. We may have evolved to sleep because it aids healing, memory consolidation, and other important processes, but we still have much to learn about the ways sleeping achieves these ends. Other roles for sleep, like conserving energy during times when it wouldn't be advantageous to be awake. For example, during scorching hot days in Death Valley, have been proposed as well. At least for now, we don't have a single, conclusive answer to the question of why we sleep. But, no matter how sleeping arose, we can probably accept that it provided a substantial evolutionary advantage once in place, since sleep is found across much of the animal kingdom. 6. Why only some thunderstorms produced tornadoes? A standard explanation of how tornadoes form is that they're spawned when cold, dry air mingles with warm, humid air. That's how we justify the fact that Tornado Alley in the central United States, where Arctic air from the southwest, and air from the Gulf of Mexico mix, has so many tornadoes. But that's not the whole story. These conditions do create more thunderstorms. But, not all thunderstorms include tornadoes. And scientists aren't sure why. In some cases, tornadoes may form as when there are temperature changes in the air flowing downward around mesocyclones, vortexes within the types of storms tornadoes can come from. This idea has theoretical and experimental support. But, even without these temperature variations, tornadoes can still form, demonstrating how much more we have to learn about the phenomenon. 7. Why we itch. At a basic level, itch is an unpleasant sensation that triggers the urge to scratch. Scratching could end up making an itch worse. But, it may also serve a purpose. Mechanical itch, the kind triggered when fine hairs on your body are disturbed, may alert you to the presence of biting insects or parasites. And scratching could brush them away. This hypothesis is difficult to test. And it doesn't cover chemical itch caused by histamine and other scratch-provoking substances. Long after you've missed your chance to brush a mosquito off your skin, histamine in the itchy bump it has left behind continues to compel you to scratch. Whether this type of itching serves a purpose, or is simply an incidental activation of the itch system, isn't conclusively known. 8. How we age. Despite what many beauty experts claim, no one really has aging figured out. Reactive chemicals called free radicals are often blamed. But, they're not the sole cause of aging. And our cells have numerous ways to help keep damage caused by excess free radicals to a minimum. Shortening of the telomeres, the protective caps of DNA at the ends of each chromosome, is another frequently cited cause of aging, but it's not the only factor. Numerous other contributors to aging have been discovered. But, no single factor explains all or even most of the aging process, making this a difficult question to answer. 9. Why we laugh. Laughter, like crying, may have developed as a social tool. Laughter doesn't appear to be a uniquely human behavior. And it may not even be limited to primates. Rats produce laughter when tickled, for example. And many other social animals, such as dolphins, make specific sounds associated with play fighting that have been likened to laughter. A leading hypothesis for why we laugh is that laughter promotes pro-social behavior by letting playmates know that the fighting is just a game. But, even if our interpretations of these behaviors are correct, it's possible that humans evolved different uses for laughter after our evolutionary splits with other animal species, making the reason for human laughter another open question. 10. How and why animals migrate back to their birthplaces. Some animals migrate to the sites of their birth to mate, a practice known as natal phylopatry, with stunning precision. Female Antarctic fur seals, for example, can return to within one body length of their exact birthplaces to breed. But, how did they get there after months or years away? One possibility is that some migratory animals navigate by sensing variations in Earth's geomagnetic field. While this makes sense given that some migratory animals, such as sea turtles, are known to be highly sensitive to these variations, it has not been conclusively demonstrated that they navigate this way. Other creatures, such as Pacific salmon, may use smell to direct them toward their breeding grounds. These fish have been shown experimentally to be able to home in on chemical cues from the water in which they develop into adult. But these chemical breadcrumbs wouldn't be detectable across the vast ocean, meaning that even if the salmon use them to navigate, they must also have a way to direct themselves close enough to the source to smell them. The complete mechanisms behind natal phylopatry, even in this well-studied case, are still unknown. 11. What dreams are for? If the question of why we sleep is complicated, the question of why we dream is even more so. Dreaming, especially with vivid, fanciful dreams, is most correlated with rapid eye movement (REM) sleep, which itself is poorly understood. One thought is that dreaming evolved to help us sort out or rehearse solutions to problems in our waking lives. But there is no hard evidence that this is the case. Although our dreams may feel significant to us, it's also possible that they serve no purpose. They may simply be a byproduct of other processes that occur during REM sleep. Studying the neurological basis of the strange and highly subjective experience of dreaming is complicated, which is why understanding the origin of dreaming is still beyond our grasp. 12. How turbulence happens. Understanding how turbulence works is incredibly important from an engineering perspective, since it affects everything from how internal combustion engines work to how far golf balls can travel. And now that most of classical physics, encompassing the laws of mechanics, thermodynamics, and so on, has long been established, turbulence is considered one of the biggest remaining problems in the field. No one has figured out a way to perfectly model turbulent flow. Modeling turbulence requires the Navier-Stokes equations, which describe the motion of fluids, liquids, gases, and plasmas. And that's the main problem. These equations themselves are poorly understood, so much so that producing a proof about one of their basic properties is one of the 7 Millennium Prize problems. It's considered one of the most important open classic questions in math, and there's $1 million waiting for anyone who can figure it out.
If you like my video, be sure to comment, like and subscribe. Press the bell icon to get notified about my latest videos.